So I assume most of you have looked at the homework assignment, right? Because it's due today, I think. So problem number 2 might seem harder than it actually is. But let's take a look at it for just a second. So we've got the typical Fitzhugh-Nagumo model, which looks like this. dv dt is negative v times v minus 0.6 times v minus 1. Obviously, we're plugging in particular values because those numbers can be, there's a range of values they can actually take on. And dw dt is equal to 0.03 times v minus 0.6 w. So that's the problem. And here's what we're being told. So 1, assume that w0 is equal to 0. 2, we're being asked for what values of v naught can you observe an action potential? Meaning, where is v of t increasing? Which, if we're careful, isn't a particularly hard question to answer. We just have to think about what the meaning means. So if we want v of t to be increasing, that's the same as saying what? We want the derivative dv dt to be greater than 0. So a lot of this is just about interpreting what the words mean. We have an expression for dv dt. So what we really want is we want this to be greater than 0. In fact, as far as I'm concerned in this problem, this second differential equation is useless, right? We don't need this at all to answer the question that's being asked. So we want this to be greater than 0. There's a w there. But we're being told what w at, so the important thing is here, right? We're being asked for what values of v at time equal to 0. And we're also being told that w at time equal to 0 is 0. So it kind of saving us, right? Like, oh, we can actually say that, sorry, at time equal to 0, we know that dv dt is given by, I'm going to be kind of super explicit here, negative v of 0 times v of 0 minus 0.6 times v of 0 minus 1 minus w of 0. Or, sorry, if you wanted to write it less terribly, you could say dv dt is equal to negative v naught times v naught minus 0.6 times v naught minus 1 minus w naught. But that is 0. And then actually answering the question, where is this? Where is that positive? Is a pretty straightforward process. We can put the places that make this equal to 0 on the number line. So v naught could be 0 or 0.6 or 1. Those are the places where the derivative is equal to 0. And then we can just test a point in each of those intervals to see where is it positive and where is it negative. So if we pick something like v naught equal to 2, we see that we get a negative number times a positive number times a positive number, which is negative overall. And if we pick something like v naught equal to 0.8, we get a negative times a negative, which is positive overall. And if we pick something like v naught equal to 0.1, negative, 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 and if v naught is equal to, say, negative 2, positive, negative, negative gives me a positive overall. So if that's what my derivative is doing, then I can see that my function is increasing here, decreasing here, increasing here, decreasing here. Which means we have v of t increasing, which means we have an action potential when, well, either here, so when v naught is less than 0, or here, when v naught is between 0.6 and 1. Which, yeah, I know, I just did the whole homework problem, but sometimes that happens. It's all right. It's not, this problem isn't about the math so much, it's about the interpretation of the words, right? This problem is very mathematically not difficult as far as it said, like third quarter calculus, right? This is a pretty straightforward question. It's more the understanding what the words mean in the problem to actually get to a place where we know what we're doing. Now, do you know what exactly in graphing linear / nonlinear systems we have to be able to do? I do not. I don't know what his expectations are for you on your final. Someone was telling me it's not cumulative. It's everything since the last midterm essentially. So it sounded like the graphing. So in fact, let's look at a similar problem to problem 1 from this homework assignment. And I'm just going to make something up, which is always dangerous, but no, it'll be fine. But before we do that, are there questions about this problem or what's going on with this problem? I just messed up so far from what we covered in, yeah. So to answer your question, let's do an example. And I want to make it so it doesn't turn out to be too terrible. So let me think about it for a moment here. So let's say we have the following system of nonlinear differential equations. So we have dx dt, and I'm going to factor it so that it's not going to be super terrible here. Let me think for 1 second here. Apologies. We have dx dt equal to, I want to go that way. And okay, sure, we'll do that. Sorry. Yeah. Brain. Just trying to not make it too complicated, but complicated enough so that it turns out nice. Let's do that. Okay, let's do, yeah. X minus 1 times y equal to 2x minus x squared. Seems a little dangerous. We'll be all right though. And then make the other one much simpler. Sure, we can go. We'll get to that in a little bit. So here are our 2 nonlinear differential equations. And first thing we're going to do, let's just graph the Nullclines. Also known as the 0 isoclines. Same thing. And I would encourage you, if you have the ability to draw them in different colors. It's going to be helpful in my opinion. So I'm going to draw the dx dt ones, Nullclines in red, and the dy dt ones in green. So notably, I already factored the first one. So I'm going to get for the first one either it's going to give me either x minus 1 equal to 0 or y minus 2x plus x squared equal to 0. So my nullclines, my x nullclines are going to be the vertical line x equal to 1 and the parabola y equal to 2x minus x squared, which is going to have, well, that's going to be, just 1 second here. There might be an issue that I want to avoid if I can help it. Yeah, there is. Let's change this just a tiny bit to make it not terrible. Let's make that an x minus 3. It's just an issue I want to avoid, that where things will be weird if it's x equal to 1. All right. And then before I start graphing things, let's also find the y ones. So dy dt equal to 0 is going to give me y times y minus x equal to 0. So I'm either going to get y equal to 0 or y equal to x. All right. I think we can fit this on this page here. 1, 2, 3, 4. So x, oh, I already made a mistake. Not a mistake, just an oversight. I should have drawn my y equal to 0, which is my x-axis, in green. So I can kind of fix that. Sure. That's very dark green. Okay. And now I've also got y equal to x. I guess I don't know the arrows there. And let's see, I've got x equal to 3 in red. And y equal to 2x minus x squared. So graphing that 2x minus x squared, I have, if I factor that, that's going to be x times 2 minus x. So I'm going to get x-intercepts at 0 and at 2. And this looks like this. All right. So here's a question I could ask that from my graph, we can see the answer. So here's the question I want to ask first. How many equilibria are there? One, 2, 3, 4, or 5. I think that would be an excellent test question. Oh, how did I get x minus 3? So if you look back, sorry, you can't see the beginning part anymore. So you look at the top, right? My dx dt was x minus 3 times y minus 2x plus x squared. So I set each of those factors equal to 0. So looking at this, yeah. Am I even, maybe I didn't go high enough. Is there, or 6? So let's count them up. There's an equilibrium at the origin. There's an equilibrium where the x nullcline crosses a y nullcline. There's an equilibrium where an x nullcline crosses a y nullcline. There's an equilibrium. Oops, this pen's dying. Where an x nullcline crosses a y nullcline. And there. This graph has 5, how about 3? 5 different equilibria. There's one at, I was going to start labeling the points. There's one at 3, 3, at 3, 0, at 2, 0, at 1, 1, and at 0, 0. But I could totally see, like, if you have, right, if you're given a graph of the x and the y nullclines and being asked how many equilibria there are just by seeing where they intersect each other. I should point out though, and I didn't draw this fully, right? So these would intersect down here, but it wouldn't be an equilibrium because that's where an X nullcline is crossing another X nullcline. And you only get equilibrium where one nullcline crosses the other type of nullcline. So, questions so far? Yeah.
Do you know how you label equilibrium? I guess my question is, how do you know you're labeling it correctly?
Sure. So I definitely have I already knew what my graphs were going to be, so I knew what was going to happen here. So only one of these I feel like is really hard to know which one it is. 0, 0 is pretty clear. 2, 0 we found when we graphed this parabola by saying, oh, well, it's going to be y equals x times 2 minus x. So we know that that's going to have an x-intercept of 2, 0. 3, 0 is also relatively clear because this line is x equal to 3, and this line is y equal to 0. 3, 3 is also, I think, not too hard to get because this line is the line y equals x. So if x equals 3, y has to be 3. This point here, I know is 1, 1 because I've plotted this parabola on this line many times. But if we actually had to do the work to find that, this is the one point here I think is kind of like, oh, we probably need to actually work to find that one. So let's go ahead and find that one just to show it. So for that nullcline, sorry, for that equilibrium, I'm trying to find the place where both of these are equal to 0. So if you actually wanted to do this without the graph, here's how you would do it. To define the equilibria, without the graph. That's totally, yeah. So someone asked, when we get our zeros, why don't we plug the values back into the equations? I did, I just didn't show my work. But let's talk about how we find the equilibria without having graphed the nullclines. I do think graphing the nullclines is a good idea, right? Like it definitely can show us where a lot of things are. So if I was working with these two equations, and let's write them down here. dy dt is y times y minus x. And I should have written dx dt first, but I didn't. And dx dt is x minus 3 times y minus 2x plus x squared. So the first equation is definitely easier to work with. Right? It's easier to see what's going to make that 0. I'm either going to get y equal to 0 or y equal to x. Sorry, you guys can see the. So then, well, actually, here I'm also going to do the same thing. I'm either going to get x equal to 3 or y minus 2x plus x squared equal to 0, which I'm going to think of as y equal to 2x minus x squared, which are really just my nullclines again. I'm just not graphing them. So to have both of these be 0 at the same time, I need to have either one of these things be true at the same time, meaning I could either have y equals 0 and x equals 3. Great, that's totally possible, right? The point 3, 0, I should probably do 3 first, right? This would give me the point 3, 0. Cool, that's a equilibrium. Or I could have y equal to 0 and the other equation over here, y equal to 2x minus x squared. So that's going to give me the equation 0 equal to 2x minus x squared. And that's going to give me two possible solutions for x. X is either going to be 0 or x is either going to be 2, which I would get by factoring this. So that gives me two equilibrium. It gives me the point x is 0, y is 0, or x is 2, y is 0. I should say two equilibria. So that exhausts all the ways y can be 0, and you get something else over here. But we can also have y equals x. So you can have y equals x and x equals 3. Oh, well, if x equals 3, y has to be 3. So we get the point 3, 3. And then finally, we have y equals x and y equals 2x minus x squared. So plugging in x for y, we get x equal to 2x minus x squared. Maybe I missed one. I might have missed one. there might be a sixth one I didn't catch. So solving this, I'm going to subtract x. We get, oh no, I didn't. I'm just kidding myself. So x minus x squared equal to 0. And factoring out of x, we get 0 equal to x times 1 minus x. So we either get x equal to 0, which would lead us back to the point 0, 0, which we already have, or x equal to 1, which would lead us to the point 1, 1, which we didn't already have. Basically, we need every possible combination where this equals 0 and this equals 0. And that's it. That's all 5 of them. Okay, so you plug in the xy of one equation, the other equation you think about, but you get just as 0 by plugging in the xy value back into the same equation used to find in the first place. I think that sounds right. Essentially, we're looking for every possible way that both equations can be 0 at the same time. And these are the 5 points that give us that. Right? If x is 3 and y is 0, well, this equation will be 0 because y is 0, and this equation will be 0 because x is 3. Or if x is 0 and y is 0, well, clearly that's 0. And if x and y are both 0, you get 0 minus 0 plus 0, which is 0. And 0 times negative 3 is 0. And the point 2, 0, well, again, if y is 0, that's 0. And if x is 2 and y is 0, this equation will again be 0 because 0 minus 4 plus 4 will be 0. And if x is 3 and y is 3, that's 0. And 3 minus 3 is 0. And if x is 1 and y is 1, that's 0 because 1 minus 1 is 0. And that's 0 because 1 minus 2 plus 1 is 0. So these are the 5 points we get that are equilibrium. I will go back to saying, if you have some funky looking nonlinear equations, and these aren't that funky, but they're kind of funky. Graphing the Nullclines is a good idea. It really does help you visualize how many equilibria you're going to have. You probably won't need to graph them if he hasn't asked you to, but it might help, right? Even if you don't have to, it could be a good thing to do. I think I bit my lip earlier. It kind of hurts. I'm like, oh, okay, drinking water doesn't feel so good. Okay. What about classifying them? That's where things get messy. So we want to classify our equilibria. So I really, I don't think I don't know. I don't want to say that because he could. If I was classifying equilibria, I would always want to use Jacobian. I find the graphical method challenging. I just don't, I'm not able to look at the thing and really see what the shape is supposed to look like. So I would say Jacobian. So let's grab our equations again. I know I just made up on the spot. So yeah, that's going to be kind of ugly. I would probably multiply that out before I found my partial derivatives. So f of xy, which is your dx dt, if we multiply that out, we're going to get xy minus 2x squared plus x cubed, and then distributed minus 3y plus 6x minus 3x squared. Kind of gross. My g of xy is much nicer. It's already multiplied out for us. It's y squared minus xy. All right, so let's find all the things. The partial with respect to x is going to be y minus 4x plus 3x squared plus 6 minus 6x, which we can combine a little bit, but not a lot. That's going to be, I would probably write it like this: 3x squared minus 10x plus 6 plus y. That's pretty fun, not gonna lie. Fy would be much nicer. It'd be x minus 3. That's a lot better. Okay. G sub x would be negative y. G sub y would be 2y minus x. So here is our Jacobian. This first part's gross. 3x squared minus 10x plus 6 plus y. And then the rest of it's fairly normal. Now, a number of these are going to be really easy to deal with because a number of them have either y equal to 0 or x equal to 3, which is good news and is pretty, I'd say it's fairly typical. It's pretty typical to have a lot of your Jacobians have a 0 in either the upper right-hand corner or the lower left-hand corner. So if you go back to our 5 equilibria, and we have, so we're going to do the following. We're going to find j of 0, 0, j of 3, 0. I forget. I mean, let me look back and see what they were, because I've forgotten what they were. Let's see. We had 3, 0, 2, 0, and then we had a 3, 3, and a 1, 1. 4 of these are easy. Easy. Relatively easy. The last one is going to be a little more work. So let's see what we get. So j of 0, 0 is going to be, zeros are nice. 0, 0, 6, 0. Negative 3, 0, 0. Ooh. Wow. So we've got what does it mean when one of the eigenvalues is 0? That's a good question. Let's come back to that. We'll circle back. Although let's see what happens. We might have multiple of these things, but we'll come back. So let's look at the next one. Let's see, plugging in 3 for x and 0 for y. 3 for x is going to be a little bit narrow, but fine. So 3 times 9 is 27, minus 30 is negative 3, plus 6 is 3, and y is 0. Plugging in 3 for x, we get a 0 here. Plugging in 0 for y, we get a 0 here. And 2 times 0 minus 3 is negative 3. Great. All of you should be able to tell me with just a moment's worth of thought what kind of equilibrium we have here. It's definitely a saddle because our eigenvalues are positive and negative. Or alternatively, because the determinant is negative. If your determinant of your matrix is negative, that is an automatic saddle. Okay, let's look at the next one. Plugging in 2 for x and 0 for y. Okay, so 2 for x, this first one's a real pain. 3 times 4 is 12, minus 20 is negative 8, plus 6 is negative 2. 2 for x, 2 minus 3 is negative 1, 0 for y, and 2 times 0 minus 2 is a negative 2. All right, this one also, everyone should be able to tell me that we have a stable node because both of our eigenvalues are negative. They happen to be the same value, that's okay. Same value eigenvalues still means both your eigenvalues are the same value, it means you either have a stable node or an unstable node because they're either both positive or both negative. That's the only thing that can happen there. It means your linear, it means your system of it means your general solution, C1 e to the lambda 1 t times v1 plus c2 e to the lambda 2 to v2. It means it condenses into something nicer, but that's okay. All right, 3, 3. So 3 for x and 3 for y, we're going to get 27 minus 30 is negative 3, plus 6 is positive 3, plus another 3 is 6. And then plugging in 3 for x, you get 0. Plugging in 3 for y, you get negative 3. And 3 and 3 means you get 6 minus 3, which is going to be 3. So we have an unstable node because they're both positive. And finally, the last one, we're actually going to have something where we have to do a bit of work. So the last Jacobian here is going to be, let's see, 3 minus 10 plus 6 plus 1, 1 minus 3, negative 1, and 2 minus 1. So that's going to be, let's see, negative 7. I get a 0 there. That's funny. So I do want to stress here, this matrix, we do not know the eigenvalues right off the bat. However, this one I can see that we can get away without finding them. Because my determinant is 0 times 1 minus negative 2 times negative 1, which is negative 2. And the determinant being negative automatically gives us what? Saddle. So the reason we don't know the eigenvalues immediately here is because we don't have a 0 on one of the off-diagonal elements. So let me rewind a little bit. If your matrix looks like this, sure. Or like this. Or even like this, where you have a 0 in either one of those off-diagonal corners, automatically we know that the eigenvalues are A and D. And I mean, you could do the work, right? We can say, well, if I want to find the eigenvalues, I'm going to do the determinant of A minus lambda I, set that equal to 0. But the determinant of A minus lambda I is going to be the determinant of A minus lambda 0, C, using this first example, A minus lambda, set that equal to 0. But the determinant of this is A minus lambda times D minus lambda minus 0 times C. So since we have a 0 there, or in both spots, that second part always ends up being 0, and you just get something that's already factored. And you can definitely tell, oh yeah, lambda is going to be A or lambda is going to be D, sorry. But in this matrix up here, we don't have that. Right? If we find it, we can actually find the eigenvalues, but it might be worth doing just to kind of point out that we can do it. For the matrix 0, negative 2, negative 1, 1, you could either do it the long way and say, okay, we're going to do the determinant of A minus lambda I. There, all of these. One, you go too high. And the determinant of that is going to be negative lambda times 1 minus lambda minus negative 2 times negative 1 equal to 0. Multiply it out and get a quadratic. So I'm going to get negative lambda plus lambda squared minus 2, or better, lambda squared minus lambda minus 2 equal to 0. And I think I lucked out. I think this does factor. So we end up getting lambda equal to 2, and lambda equal to negative 1. Or we could use the trace determinant method, right? Trace is 0 plus 1. Determinant is 0 minus negative 2 times negative 1. And then you could find the eigenvalues by doing lambda is the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2, which in this case would be 1 plus or minus the square root of 1 minus 4 times negative 2 all over 2. And I do want to emphasize here, specifically because the determinant is negative, this, first of all, the inside of the square root has to be positive, because you have a positive thing minus a negative thing, which will end up being a positive thing. And importantly, this square root is bigger in size than this number here. So when you add it, it gets bigger, and when you subtract it, it gets smaller. So if it was already positive, you're going to subtract the bigger thing and you'll get 1 positive and 1 negative. If it was already negative, you're going to add a bigger thing and you'll get 1 positive and 1 negative. So because the determinant is negative, you are automatically guaranteed to get real eigenvalues that have to have opposite signs. Meaning when your determinant's negative, you can always jump straight to the conclusion that you have a saddle because your eigenvalues have to be opposite signs. So determinant being negative automatically gives us a saddle. It's kind of great. I would definitely look out for that because I have to imagine he would accept that line of reasoning as justification. Like I don't think you would require any more proof. So if you can see that the term being negative gives you a saddle and he's asking you to classify something, done, right? You don't have to spend more time or mental energy on that problem. All right. So I had said something about an eigenvalue being 0. Yeah. I know I did a problem like that last year sometime, and I'm trying to remember what, like, I don't honestly remember like what it actually means when eigenvalue is 0. I think I have an idea of what it means, but I'm not 100% sure. I'm not sure if it's the best way to spend our time though. But no, I think, what do you guys think? Do you want to hear about eigenvalue being 0? It's okay if you say no. I really don't mind. It's okay if you say yes as well. Right. So the problem is I have to like actually think about it to figure it out because. Okay. I feel like it's kind of, so if you were all in Tim Lewis's class, I would say we should definitely talk about it because it's definitely a question he likes to ask because he feels like it's easier. But since you're not in Tim Lewis's class or Ron Walker's class, my bet would be let's explore it in a different context, just for a few minutes here. So let me make up. Well, sure. So let's say we had this system of equations, this linear system of equations. Let's say we had it's pens. You're not my favorite pen. Problem is I see all the ink in these pens. I'm like, I know there's ink in you. Why don't you want to write better? You wrote so nice at the beginning. I was so excited. You guys remember I got new pens? I was like, yeah, new pens. And then I was like, oh, okay, fine. You aren't the pens I hoped you would be. Let's say we have the following system of equations. And I want to get a 0 there. Okay. Yeah, so this is going to be kind of funky. Let's say we got the following. So here's our linear system of equations, which is not very exciting. And if we take a look at it, we're going to have the matrix 3, 0, -2, 0. All right, so our eigenvalues are going to be and 3 and 0. All right, let's find our eigenvectors as well. So when lambda equals 3, the eigenvector is going to look like, let's see here. I know it's been a while since we've done this. A times the vector should equal 3 times the vector. So if we, let's see, so we're going to have 3x equal to 3x. That's not helpful. Right, 3x equal to 3x. Well, yeah, that's always true. X could be anything at this point. So we need to use the second equation that -2 times x equals 3 times 1. Okay, that's more helpful because now I can say that I would probably just go straight to saying x is 3, y is -2. That's the easiest way. Just let each variable be the other one's coefficient. So 3, -2 is my eigenvector there. Now I think the other eigenvector is not particularly interesting. I could be wrong though. Let's find out. So now I'm trying to solve 3, 0, -2, 0 times xy equal to 0 times xy. So 3 times x needs to equal 0. Okay. Well, x is 0. And if x is 0, what does y have to be? Anything else except for, right, y can't be 0. Does that correspond to what we've got? Is that going to work out when I try and do this? It is. if we're careful, right? If you're not being careful, you might actually make the mistake of saying you're going to have -2 times y equal to y. But that's not what we have. We have -2 times x still equal to 0. So we're again just getting x equal to 0. There's no condition on y. Y can be anything. So we're going to let y equal to 1. So our eigenvector here is 0, 1. Okay, but the fact that lambda equals 0 means something. So what I really want to do is, I really want to show you the graph of this, because I think that's the most helpful way to see what's going on here. Let me grab that just one sec. So I remember always being kind of thrown off by this situation here. Where's my graphing stuff? Oh, that's interesting. I didn't do that. Okay. So let me do these real quick here. So dx dt is 3 times x. dy dt is -2 times x. And let's see. Yeah. Exactly. Cool. Okay, good. What if that happens? I was like, I hope this is what I think it is. All right. So what happens here is essentially everything is moving away from the origin, but in fact, let me draw it here. So here's what we've got. So one of our eigenlines was the eigenvector 0, 1. So this is one of my eigenlines. V2 equals 0, 1, but the eigenvalue is 0. Sorry. My other eigenline was V1 equal to 3, -2. Or if you prefer, -2x equals 3y, which means y equals -2/3 x. So when I draw that line, well, I go over 3 and up 2, or over 3 and down 2, sorry. So and I maybe do this maybe just very slightly misleadingly. I don't want these here. But I do want these arrows here, because along this eigenline, my lambda is positive. It was +3. So if I start at this point here, I'm just going to go in that direction. But here's the interesting thing about this case. This has no influence on what's happening because the eigenvalue is 0. So what happens is no matter where you start, if you don't start like on here, you always end up getting pushed in exactly the direction of the other eigenvector. This eigenvector has no influence at all. So if you look back at the graph of this, what you're seeing is no matter where you start, you're exactly moving in a direction that's parallel to the only eigenvector that matters. Even if you start like on this here, you just get pushed away, away, away. It's kind of interesting. So when one of your eigenvalues is 0, if that happens, what essentially happens is that thing doesn't matter. And you do have this sort of either, so the stability or instability completely depends on the other eigenvalue. So this one is totally unstable, right? Because one of our eigenvalues is positive. On the other hand, if we had changed that so that it was a negative number times x, now we're stable. Right? Everything is pushing us towards this eigenline here. Kind of interesting. All right, enough about that. I would say don't worry about that too much. It's just I felt like since we saw one being 0, I should at least mention, okay, this still kind of happens.
If one of the eigenvalues is 0, then that eigenvalue will depend on the direction of the other.
Yeah, so really, when one of them is 0, it's kind of just that the other one's the only one that matters. I feel like someone asked a thing over here. No. Someone asked a question that I guess I kind of missed it. What if there's no y value, like the one on homework, there's no y value, only the x values? I'm not sure. I'm assuming that question was about, I guess I'm not sure what that question's about. Sorry, so to the person that asked that question, apologies, one sec. Oh, they seem to no longer be here, so I guess we'll never know. Oh, wow. Sorry, I missed your question, person who left.
What if the trace is 0?
What if the trace is 0? So that happens sometimes, right? So if the trace is 0,
the one that we did, where we got shadow, the one that is 0,
mm-hmm.
shadow, but the trace is 0.
Right. So if the trace is 0, a few different things can happen. So let's think about it this way. Oh, sorry, you guys want to see what I'm writing maybe? Here's the way I would answer that question. So if the trace is 0, let's look at finding the eigenvalues using the trace determinant method. Meaning if the trace is 0, my eigenvalues using the quadratic formula are going to be the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. But if the trace is 0, a lot of things are going to go away, right? That's just going to equal plus or minus the square root of -4 times the determinant all over 2. So it looks like a couple different things can happen. Either, case 1, if the determinant is negative, well, if the determinant is negative, you already know what happens. Determinant is negative, what do we get? Saddle. And that's still going to make sense here, right? If the determinant is negative, let's just pick a number to make it easy. Let's say the determinant is -9. Then our eigenvalues will be plus or minus the square root of -4 times -9 all over 2, which is plus or minus the square root of 36 all over 2, which is plus or minus 6 over 2, which is plus or minus 3. Oh yeah, if the determinant's negative, we have to get eigenvalues that are opposite signs and both real. Or the determinant's positive. Well, in that case, we're going to get plus or minus the square root of a negative number. Again, let's just pick a number. Let's say our eigenvalues were both, our determinant was +9. Then our eigenvalues are going to be square root of -36 over 2, which is plus or minus 6i over 2, which is plus or minus 3i. So if our eigenvalues are complex conjugates, but are purely imaginary, we're in the one kind of weird case where we don't have an outward spiral or an inward spiral, we have a center or a neutral spiral. So we have a neutral spiral. So those are the two things that can happen if your trace is 0. If your determinant's positive, you have a neutral spiral. If your determinant's negative, you have a saddle. Can we go over graphing a spiral? Sure. We can go over what I think. So here's what I think we want to do. Let's go over how to determine the direction of the spiral graphically, which I think might be what you maybe really mean. I think. Okay, great. So we'll do that. And then, yeah, a couple people have asked about 3A. So yeah. So we need one that actually is going to be a spiral, which means the determinant needs to be positive. So let's look at something like this. Let's say we have dx dt equal to, I'm really just going to make up stuff and hopefully it comes out. Well, I'll make sure it comes out right. But let's say we have 4x, okay, minus 2y, and dy dt is going to be 3x plus y. So there's my, I know yours is probably going to be nonlinear, but we'll deal. So I want to classify the equilibrium, which is just the origin, right? If it's a linear system of differential equations, it's definitely just the origin. And also, what direction is it? If it's a spiral, which it is, because I know it's going to be a spiral because the determinant is. Oh, actually, I don't know it's going to be a spiral. So right, because if the determinant is positive, it could be a spiral or it could be a node, right? If the determinant is positive, it has to be. So, well, we'll see what happens here, and if it's not right, we'll fix it in the next one. So let's find our eigenvalues. So my trace is 5. My determinant is 4 minus 6, which is 10. I'm feeling pretty good about this being a spiral. Why am I feeling good? Well, because I know that to be a spiral, this has to be negative. And it is. Right? What's the word for that thing? The discriminant of my root has to be negative. So here are my eigenvalues. It's going to be 5 plus or minus the square root of 25 minus 4 times 10 all over 2. And I don't particularly care what they are. I just care that they're both imaginary. So I'm getting 5 plus or minus the square root of negative 15 over 2. All right, so we definitely have a spiral. Stable or unstable? Unstable, because our trace is positive. All right, which way is it going? I have no idea. I know there's a way that you can look at this corner here and say if it's negative, it's one way, if it's positive, it's the other way. I have it on a Post-it note on my computer at home. I couldn't tell you. I've looked at that Post-it note 1,000 times. I couldn't tell you what it is. So, and really, it's not the best way of doing it, right? Memorizing a thing that's easy to forget is never the best way to do it. What you want to do is then pick a few points. I personally like to choose the points, the corners of the square that are negative 1, 1, 1, 1, 1, negative 1, and negative 1, negative 1. So I'm just going to plug in 1, 1. If I plug in x equal to 1, y equal to 1, dx dt is 4 minus 2, dy dt is 3 plus 1. So that means at that point, I'm going over 2 and up 4. So notably, I'm more up than down. Okay, from that one piece of information, I'm pretty confident I know what's going to happen. It's going to go counterclockwise because I'm on this side of the line, y equals x. Kind of funky, but let's do a few more just to be sure. So if x equals negative 1 and y equals 1, dx dt is now going to be, sorry, negative 1. I think I said it backwards. That's all right. If x is 1 and y is negative 1, I'm going to get 4 plus 2 for dx dt. I'm going to get 3 minus 1, so 2 for dy dt. So down here, I'm going 6 in the x direction and 2 in the y direction. So more right than I'm going up. Right? Over 6, up 2. Approximate. If x is negative 1 and y is 1, I'm going to get dx dt is negative 4 minus 2 is negative 6. dy dt is negative 3 plus 1, which is negative 2. So I'm going left 6 down 2. I'm going that way. And finally, at this point here, negative 1, I'm getting negative 4 plus 2 and negative 3 minus 1. So I'm going 2 left, 4 down. I mean, that definitely looks to me counterclockwise, right? It'd be hard to like imagine you're starting here and you're ending going that way. That seems just wrong. So drawing these arrows can usually help you figure out which way you're going. And really, the truth of the matter is, if you start doing this, and you start at the point 1, 1, it's pretty easy to know what's going to happen based on where you are compared to the line y equals x. So if you start at 1, 1, and your arrow is on this side of the line y equals x, you're going to be counterclockwise. Then you could be pointing that way, or you can be pointing that way. You're still going to be counterclockwise. Because you're essentially traveling in a direction that's going to lead you around the origin on this side of the origin. Whereas if you end up going some way in this direction, that's going to be clockwise. I would encourage you, if you're asked a question like this, to draw more than just one arrow to kind of justify your thought process. But really, unless I've done this a number of times, I don't think I'm off base here. I have noticed that this is always the case because of how you're going, right? If you're going this way, you're going to eventually end up going around the origin that way. And so I guess we could go back and say, all right, if you have a spiral and it's negative in this corner, it's counterclockwise. And if it's positive in this corner, it's clockwise. You can do some Googling if you wanted to, because that's actually what I did when I was like, how do you know when it's clockwise or counterclockwise? I Googled it, like, oh yeah, in the matrix, if it's positive or negative here, it's one way. If it's positive or negative here, it's the other way. That's the way I actually found it. But it's probably best if you actually do some graphing things. That's the way I would expect my students to have shown me, other than just having memorized the fact. Okay, let's look at problem 3a. I'm going to change it. I'm gonna not do all the homework problems just so I can feel like I'm doing my job correctly. So let's change the numbers a little bit. So this is very similar to the problem we did a few weeks ago where I was talking about students of various types, but let's say there is a group of, sure, I can change the numbers, 60 people from 5 different countries. And yes, equally divided, 12 people from each country. How many ways can we make a committee of 8 people if all 8 must be from the same country? Really, the whole point of this question is just to make it easier to answer the second part of this question. So there's not a lot, there's a lot of options, but not really a lot of options. So let's say our country, I don't care. So country A, country B, country C, country D. So I want all the people to be from country A. Well, there's only 12 people who are from country A, and there are only 12 choose 8 ways of choosing 8 of them. And the same is true for each other country. There are 12 choose 8 ways of choosing 8 people from country B. There are 12 choose 8 ways of choosing 8 people from country C, and 12 choose 8 from country D. Now, here's the question. Are we multiplying these or adding these together? We're adding. Why are we adding? Well, I don't want 8 people from country A and 8 people from country B and 8 people from country C and 8 people from country D. I want one or the other or the other or the other. So I want 8 people from country A or 8 from country B or 8 from country C or 8 from country D. Which I would then write as Oops, I missed a country. Right, there are 5 countries, not just 4 countries. Better add on country E here. Country E, there's also 12 choose 8 ways of doing it. So we're going to get 5 times 12 choose 8. Somebody asked, with these problems, how do you know where to start? That's a good question. Usually I'm going to start by kind of saying to myself, well, what are they asking for? And this first question is, how many ways can we make a committee of 8 people if all 8 must be from the same country? That's kind of the main indicator here that, oh yeah, if they have to be from the same country, that's telling me, well, I have 12 from the country, from any one country, and I'm choosing 8. That's the piece of information that's leading me to get to this. But there's not like a one-size-fits-all answer for that question. It really depends on the context of the question. I would say knowing where to start is based on careful reading of the question and really making sure you understand what they're asking for. The second part of this question is definitely based on the first part. So the second part is asking, what's the number of ways? So I'm going to say, what's the number of ways of having an 8-person committee with at least 2 countries represented? Now, a lot of the time, if you see a question that says at least this many things, the idea is frequently going to be to use the complement. Meaning, if I want at least 2 countries represented, well, that means I could have a committee of 8 people where there's 7 from one country, 1 from another, or 6 from one country and 2 from another. But you can also have 3 countries represented, or 4 or 5. That's a lot of things to figure out, right? The intent here is not to be like, well, okay, if I want 2 countries, that's going to, I mean, even just the 2 country part, if I wanted exactly 2 countries, that would be problematic. Exactly 2 could be, well, I want 12 choose 7 times 12 choose 1. That's what I have, 7 from one country and 1 from another. And then I could have 12 choose 6 times 12 choose 2, plus 12 choose 5 times 12 choose 3, plus all the way down to 12 choose 1 times 12 choose 7. Times, because this is all the way of just having like country A and country B. You could have 7 from A and 1 from B, or 6 from A and 2 from B, or 5 from A and 3 from B, et cetera, et cetera. But then there's actually 5 choose 2 ways of picking the countries. It could be A and B, or A and C, or A and D, or A and E, or B and D and B, right? And then you also have to do that same process, which even more complicatedly, for having 3 different countries represented, right? It would be 12 choose 6 times 12 choose 1 times 12 choose 1, plus 12 choose 5 times 12 choose 2, right? There's a lot of ways of getting 3 different countries represented. You could have 5 of one country and 2 and 1, or 3 and 3 and 2, or, right? It just gets very complicated. So the whole point here is to be like, well, there's an easier way to do this, right? If I want the number of ways, or the number of committees with at least 2 countries represented, well, here's what we know. We know that the number of ways of one country, which you just found, plus the number of ways of 2 countries, plus the number of ways of 3 countries, oops, there's a 3 there, plus the number of ways of 4 countries, plus the number of ways of 5 countries. That's equal to all the ways. Right, those are the only possibilities. 1 country is represented on a committee, or 2, or 3, or 4, or 5. But there's only 5 countries attending this conference, so that's it. Well, we just were asked to find this. So of course, we're going to say, well, what we want, the number of ways of at least 2 countries is equal to all the ways minus the thing we just found, which was 5 times 12 choose 8. Oops, sorry, you can't see that. So now we have to figure out all the ways, and all the ways is easy. All the ways is, well, I'm trying to make a committee of 8 people. If I can literally choose any of the 60 people I want, there are 60 choose 8 ways of doing that. And there's absolutely no reason to actually find the numbers here, unless you were specifically asked to do so. For the example, now, even for the example you have on your homework, I feel like the numbers are large enough that you should probably leave your answer like this format, but if you really wanted to, you could find it. If you're trying to do something like 60 choose 8 on a calculator, a lot of calculators do have a button that looks like NCR, where you first type in 60 and then hit the button NCR and then hit 8 and then hit equals, and that'll give you 60 choose 8, which is whatever it is. So if you're actually trying to find the number and not just write this expression, that's an easier way of doing it. Or you could or you could actually say, okay, 60 choose 8 is 60 factorial over 8 factorial times 52 factorial. And then that's just going to be just 60 times 59 times 58 times 57 times 56 times 55 times 54 times 53. Right, if you really have to do it and you don't have a fun button on your calculator, that's what you would calculate to do 62. It's kind of a giant pain in the butt, but it works.